Hello everybody, in this video we will be discussing broadcasting in NumPy. So you might have already seen a few examples of this in previous videos, and today we're going to be working through a number of examples all from the documentation. So let's first start by talking about, well, what is broadcasting? And you can think of it as how NumPy deals with adding, multiplying arrays of different sizes. So for instance, let's say I have this array here. What does it mean to add it to this array? And the big idea is that if we impose a few compatibility constraints, we should be able to stretch smaller arrays to the dimension of larger arrays. One nice thing about broadcasting is this is a vectorized operation, like a lot of things in NumPy. So what this means for us is that it's very fast and a good choice for many things that we might want to do. All right, so kind of the easiest case to understand is if the arrays we're working with have the same dimensions. So just as an example, let's say I have this array here, 1, 2, 3, and let's say I want to add it to the array 2, 2, 2. So they have same dimensions, and the way things work in this case is all of the operations are done element-wise. So I'll make a note of that here. So operations are done element-wise. So in this case, we have 1, 2, 3 plus 2, 2, 2. So what we do is we look at the first entry. We have 1 plus 2, that's going to be 3. Then we have 2 plus 2, that's going to be 4. Then we have 3 plus 2, that's going to be 5. Similarly, we can do multiplication. So let's pick the same example. So I have 1, 2, 3, 2, 2, 2. 1 times 2 is 2. Now let's look at the middle element. 2 times 2 is 4. 3 times 2 is 6. So in the case where the arrays have the same dimensions, you just do the operation element-wise. So when we get to kind of broadcasting with different dimensions, keep this basic example in mind, because our goal is we're going to think about stretching the smaller array to fit the dimension of the bigger array. So one more example that's not too tough to think about is, let's say I have 1, 2, 3, and I want to multiply it by the scalar 2. So kind of the intuitive way of thinking about this is, okay, well, what if I just multiply 2 across the board? So I have 1 times 2, that's 2. 2 times 2 is 4. 2 times 3 is 6. So this works fine for the scalar example, but soon we're going to be working with arrays of different sizes, not just kind of with scalars. So the way that you want to interpret this actually is a little bit different. So what I'm going to do is let's really think about this 2 as stretching to fit this the dimensions of this larger array here. So let's think about this as like a 1 by 3. So what I mean by that is let's really think about this computation as this larger array. Let me just copy it, paste it. And now what I'm going to do is I'm going to imagine that we stretch this 2 to be the same size as this larger array, this 1, 2, 3 array. So this is going to look like 2, 2, 2 from the first slide, or the previous slide. And again, now we have arrays of the same size, and we can do the element-wise multiplication. So now we can have element-wise multiplication. And again, like I mentioned, this is kind of, we want to think about this as like a stretching. It's important to note, so this stretching analogy, this is purely just for our understanding. NumPy itself does not make copies of arrays. It's done a lot more efficiently, but this is how we want to visualize what's happening. So at least in the scalar case, and we're going to see a few more examples in a moment. So let's get into a couple of general rules. So what we want to do is, let's say I want to add or multiply two arrays and they're different shapes, let's say. So what you want to do is you want to compare the shapes of the arrays. So for instance, if I had a 3x3 array, the element-wise shape would be 3, 3, and starting with the rightmost dimension. So if this sentence was a little bit confusing, let's do an example together. So let's say I have an image that's kind of like the object I'm representing. And let's say it's made of 256 by 256 pixels, and each pixel contains RGB values. So this 3 here, you can think about this as the red, green, blue values. So the image, how it might be stored in a NumPy array is this might be written as like 256, 256, 3. And what we want to do is when we compare this to another array, we're going to start here looking at the rightmost value. So that's going to be 3. So we're going to go 3, then we're going to look at 256, then we're going to look at 256. Now imagine that for every RGB value, I want to scale it by some quantity. So let's say I have like a scaling parameter, a scalar. And this scalar is going to contain RGB values. So let's say it's just 3 here. How this might be represented in NumPy is you might get the dimensions like 3, like this, or it might be dimensionless, for instance. So it might pop up as something like this. In any case, what we're going to do is we're going to compare starting from the right. So this 3 here under scale, we line it up with the rightmost value from the image dimensions. So once we kind of understand how to set up looking at the dimensions, now we can start comparing them. So we say that 2 dimensions are compatible if one of the following is satisfied. Either both of the dimensions are equal or one of the dimensions is 1. So you might get a little bit nervous here that there's no kind of 1s, but that's not a problem because we can really think about this as just putting a bunch of 1s in front of this singleton 3. But let's start by looking at the rightmost values. So we have 3 and 3. So that's going to stay a 3, and that satisfies the first rule. So 3 and 3 are equal to each other. Next, what we're going to do is we're going to prepend a 1 for every dimension we're missing. So now we have 256 and 1. So these are not equal, but it does satisfy the second rule. One of the dimensions is 1. And the way we want to think about this is the dimension that's 1 is going to get stretched to be this 256. So our result here is going to be 256. And then again, for the missing dimension, we prepend a 1. And same story here, we have 256 and 1. So the 1 gets stretched to be the 256. So you can think about this again in that scaling example we looked at. Let me scroll back, where this 2 gets stretched to be the same shape. All right, so these are the general rules. Let's do a couple of examples. So this is a really nice example. Again, it's from the documentation because it's showing you explicitly here. So we have A is a 4-dimensional array, B is a 3-dimensional array. And so something to notice is the arrays definitely don't have to have the same number of dimensions. But another nice thing about this example is we'll see that A has dimensions that are going to be stretched and B has dimensions that are going to be stretched. So let's keep the rules in mind, and remember we're going to read from right to left. So rightmost here, we have 1 and 5. So they're not equal, but this is 1. So what's going to happen is the 1 gets stretched to a 5. So 5 stays here. Now let's look at the next dimension. We have 6 and 1. The 1 is going to get stretched to a 6. 1 and 7, the 1 is going to get stretched to a 7. And then remember, so if there's a dimension that's missing, we just put a 1, and what's left over is going to be 8. So our result after doing our arithmetic operation, so maybe addition, multiplication, is going to be an 8 by 7 by 6 by 5 array. So let's take a look at a couple more examples. So here I have just a bunch of different shapes. So let's say A is a NumPy array, B is a NumPy array, C and D, etc. These are all NumPy arrays. And we call like their shape. And we can see here, okay, these all have different shapes. I briefly mentioned earlier this kind of empty parentheses. This represents a scalar. And if you're a little bit confused about this 6 comma blank, this happens if, for instance, you pass a list and convert it to a NumPy array. It thinks of that as having one dimension. There are ways of kind of kicking it up to be 2 dimensions and keeping it looking pretty much the same, but not super important for this video. And an important terminology is we say that A, B, C, and D are all what we call broadcastable to a 5 by 6 array, meaning that we can do arithmetic with A, B, C, and D if the array is 5 by 6. So I'm going to go through each of these and show you exactly how that works. So let's take a look at A. So remember we said A is 5 by 1, so we have 5 rows, 1 column. And what we do is, so this dimension here, remember we want it to be to kind of play nicely with 5 by 6. So think about it, this 1 needs to get stretched to a 6. So what we're going to do is we're going to copy this column so that we get 6 total. So this is exactly what this notation here is saying. It's saying take every row in this first column, and we're going to broadcast it so that there's 6 total columns. So another way of thinking about this is A, if we want to broadcast it to a 5 by 6 array, this is what it's going to look like. So now if you hand me another 5 by 6 array, I can add them, I can multiply them, and all of that's going to be done element-wise. Similarly, let's say we have B, which is a 1 by 6, and very similar to in the case of A, we're going to broadcast this row so that there are 5 total. And this is, again, how B can act like a 5 by 6 array. So for instance, A can act like a 5 by 6, B can act like a 5 by 6, and this is how we could broadcast them together. So again, just so I make it clear, remember we said A was 5 by 1. Here's A. B is 1 by 6. And using our general broadcasting rules, we can see, okay, 1 and 1 becomes 6, 5 and 1 becomes 5. So our resulting array is going to be a 5 by 6. So now we have C. Remember, C is kind of, this dimension is a little bit strange. You can really think about it as a 1 by 6. So 1 row, bunch of columns. So you can think of it as looking very similar to B. So it acts like a 1 by 6 array, but B is a 1 by 6 array. So then we know, well, 1 by 6 can act like a 5 by 6. So it's really the same story as what's happening in B, just in a slightly different way. So again, this might happen where if you turn a list into a NumPy array, for instance. And lastly, let's say we have a scalar, so this empty dimension tuple. So let's say our scalar is 3. And to make it act like 5 by 6, well, all we do is we take a 5 by 6 array and we just fill every value with 3. And just to finish off, let's take a look at something that's not an example, so where we can't broadcast one to the other. So here we have this 4 by 3 array. And if I want to add it to this 1 by 4 array, well, that's not possible because, yes, I could stretch this to be length 4 like this, but the issue is that I don't have any way of kind of removing this element here. I don't have any rule for telling me how do I kind of go across the rows like this. So this is an example where you wouldn't be able to broadcast and you would get an error. All right, I think this is a good place to stop. Thank you for watching, and I'll see you in the next video.